Okay, everybody, let's talk about the 1800s lab.
What?
The lab as it existed in the 1800s.
Oh.
The laboratory?
The laboratory. Here's what they had in the laboratory at that time. Okay? They had glass, and they had silk, and they had wool or fur or cats. They had rubber. They had wood and thread and metal rods with wood handles. And they had metal spheres on insulating stands. And that's about it. Okay?
Wow, high tech.
Very high tech. Now, with that little amount of material, you can discover the concept of charge. Okay? You can discover the concept that there are, you might not know, you might give it a name for something, but you know something's going on. You will be able to discover that there are two types of charge. Okay? You'll be able to discover that some things are neutral and some things are charged. You'll be able to discover that things like repel and opposites attract, right? Because you'll find that when you rub some materials together, that they'll attract some things and repel other things, right? Okay? Like you take a balloon and rub it on your cat.
Oh, that was fun.
Balloons will repel each other if you do that because they have the same charge.
You
You take a cat and rub it on your balloon. Okay? All right. You'll be able to figure out that actually if something is charged, it will attract anything that's neutral. It'll attract the opposite charge, but it'll also attract things that are neutral. Do you remember why things are attracted neutral?
Because they realign inside the
Yeah, because remember, even on the atomic level, if you have a nucleus and your electron cloud out here, that if I brought a positive charge up here, then this would shift. And the electron cloud would look like what now?
Like that.
Yeah, it's going to shift over this direction where you'll have more negativeness on this side more often than you would on the other side. Okay, so even on the atomic level, you can have polarization. Okay, this is polarization. Now, we see this in big objects real easy, in a metal object, because the electrons, you know, the electrons in metals are like a sea of electrons that can float around easily on the surface, right? So if I brought a big plus here, then the electrons, more electrons would congregate on this side of the object, leaving this side more positive. Okay, now you remember when we draw these diagrams, we're not saying that this side is only electrons, this side is only protons. We're just saying there's more electrons over here and more protons over here, right? Okay. All right, in an insulator, we get this kind of behavior. On the atomic level, the electron clouds shift to polarize. In a conductor, it happens over the entire object, where the electrons physically will move to a new location. Okay? All right, you will learn about conservation of charge. Okay? Because as you rub that silk against the glass, you'll find that the silk does one thing and the glass does another thing. Okay? Like for instance, if you take a glass rod and rub it with a piece of silk, okay? And then you take that one and hang it up by a string so it's free to move, okay? If I take the glass rod and hold it, so I take this glass rod and rub it with the silk, and then take this glass rod and rub it with the silk. If I take this glass rod and hold it next to that glass rod, what's going to happen? They'll repel because they'll have the same stuff, right? They'll both be positive or they'll both be negative. If I take the silk and hold it next to it, it's going to attract. So you get this idea of conservation of charge because beforehand, both of them did nothing. They were neutral, okay? So we have conservation of charge, all right? Blah, blah, blah. Oh, you can learn that the force is inversely proportional because the closer you get the glass rod to this glass rod, the larger the force gets, and you can actually measure the angle if you'd like, and you can work backwards with statics in forces and show that the angle is varied with the radius squared. Okay? So you learn all these things by doing very little. Also, you learn also about conductors and insulators. Okay? That if you touch objects that are conductors, they share charge. If you touch insulators, they don't share all their charge, just the part that's in contact, just that little local area. Okay? All right? Okay. So you can learn a lot, but you have no idea why, okay? Because you don't know what an atom is yet. And so Ben Franklin named these things positive and negative, right? Because they reminded him, the math of it reminded him of positive and negative numbers. And they thought at the time that it was a fluid that would move in and out of the object, either an excess of the fluid or a lack of the fluid. So the lack of the fluid they called negative, and an excess of the fluid they called positive. Now it would have been nice if they'd have called those opposite, because our sign convention's all wacky now, because they assumed that it was the positive moving around, and it's really the negatives and solids that's moving around. Okay? But oh well, we're stuck. All right, so let's talk about our atom for a minute. Atom. All right, size of the atom. How big is this? And how big is this? Do you remember? This is 1 angstrom. Remember that from last year?
Oh, water.
Remember how big an angstrom is? The atomic unit of measure? 10 to the negative 10th meters. And the nuclear size, how much smaller? Oh, you remember nothing. Come on. 10 to the negative 6. That's bigger than the atom itself.
19?
14th meters. Okay? About 10 to the negative 14th meters. Okay, do you at least remember the size of the charge?
Negative 1.602 E minus 19.
Alright. Okay, I'll put plus or minus depending. A lot of times they'll just call this the electron charge, or the magnitude of the electron charge, and they'll leave it positive. Okay? A lot of times they do that just because electrons are easier to get a hold of. Okay? Alright. Okay, please note that the proton and electrons are particles of matter and they follow Newton's laws, okay? As they move around, okay? Yes? Ooh.
You're in the way of me.
Alright. Electrons don't just magically jump from one object to another, they need a pathway, okay? Alright. Charge is quantized. We talked about that. Here, let's do a little chemistry tie-in. You know what that is, right?
Yeah.
You better, from chemistry.
It's a rectangle that's
Alright, we have nonmetals and metals, right?
yeah.
Okay.
I don't.
Nonmetals tend to do what with electrons? Keep them or steal them, right? So these over here tend to be negative ions, right? And these over here tend to be positive ions, right? All right. When charge moves from one place to a new place, okay, the charge just doesn't disappear. So we have one of the many conservation laws. Conservation of charge, okay? The charge you have at the beginning equals the charge you have at the end. It doesn't just disappear somewhere, okay? So we have conservation of energy, we've got conservation of momentum, we have conservation of angular momentum, and now we've got conservation of charge, all right? Okay, what's the difference between insulators and conductors?
Charge can really flow. And they
metals make wires and non-metals don't make wires, right?
Yeah.
All right. Has to do with those valence electrons on the outside, right?
Yeah.
Okay, if the valence electrons are held tightly, then it's going to be a non-conductor, right? If they're held not so tightly, then they will be a conductor. All right. All right. If you put charge on an insulator, it stays put. It does not move around. By our definition of what an insulator is, in theory, it doesn't move at all. Okay? But if we have a metal and we were to put a bunch of, here, let's do negatives, a bunch of negatives and place them right there, what will they do?
Spread out.
Okay, they will spread out. Now, they spread out to the surface only.
Yeah.
Okay?
Is it a hollow?
It doesn't matter if it's hollow or not.
Really?
They will spread out to the surface, and there will be no net charge on the inside. And if the surface, if the object has sharp corners, then more of them will congregate here. Good question. Why? Okay, why is getting further away important?
Takes less energy.
Yeah, there's two ways you can argue it. One, you can argue it this way. Okay, in this, if you want to eliminate as much force as possible, it's like if you're being pushed somewhere, then you will move in that direction, right? So these are pushed, okay? And the thing that makes the most difference in this equation, because it's squared, is the radius, or the distance from each other. So they will try to get as far away from each other as possible. Now that seems kind of counterproductive right here, because now this one is much closer to these over here, right?
Yeah, it's farther away.
Yeah, but it has made itself a lot farther away from these, right? So overall, it has decreased the net force on itself by moving to corners, okay? They'll actually be a function of where these things will be congregated. It's not like there won't be any on the sides. There will be, but they'll just be more in the corners, okay? Another way to explain it is that it will try to get rid of as much potential energy as possible, right? Remember, potential energy, when it's able to, it converts itself into kinetic energy, right? And it will evaporate into kinetic, okay? And so if you place them all right here, they'll all rush away from each other, and this happens to be a lower energy location than this right here, okay? Lower potential energy. There won't be any at all inside. None. None, nada. And the reason why is this. This is called electrostatic equilibrium right here. This is the equilibrium condition. It's all on the surface. This is for conductors. If this is not a conductor, if it's an insulator, then they'll just stay, okay? Because they can't move. For a conductor, they're all going to move to the outside with no charge inside. No charge inside at all, okay? Now, think about why that is. All right, if there was a charge here, it would produce a net charge inside, and it would produce an electric field, right? An electric field, if you have a charge in an electric field, what's that going to produce?
Close.
If I have an electric field and I put a charge in it, what's that charge going to do? Move. It's going to move, right? And since it's in a conductor, it will move. Okay, so here's the deal. When all the charges stop moving, that implies what for the electric field?
It's gone.
There is none. That's right. It goes away. So that means if there's no charge moving anymore, that means that there can be no electric field on the inside. The electric field inside equals 0. And if there's no electric field inside, that implies that there's no net charge inside. Now there are positives and negatives inside the object. It's just that they're equalized out so that there's no electric field left. Because if there was still an electric field, because of a net charge, then we would have motion. But since there's no motion of charge anymore, there's no electric field, therefore no net charge inside. Does that make sense? Okay. So anytime we have static charge, that means there's no electric field inside of the conductor. On an insulator, there could be lots of electric field inside here. They just can't move. All right? By the way, that means if we have a wire
It only moves
and we have charge inside this wire, and we want the charge to move through like light bulbs and things like that, that means that there has to be an electric field inside the wire, right? So there is an electric field inside the wire. When we have current flowing in circuits, there's electric fields inside the wire. Now we didn't talk about that last year, but like if we have a circuit like this, then there is literally an electric field that goes around pushing the charge around.
Mr. Bruin, isn't wait.
You can do it.
Okay, oh yeah. Isn't a wire a conductor, like copper wire?
Yes.
A conductor, but do you just say that
Okay, now, let's make sure we get the difference.
Statics.
This is a wire where we have an electric field in it and we have charge moving. Here's a conductor like copper, but here we're in electrostatics, and so the charge is stationary. It's reached equilibrium. Okay, so let's write that down. Electrostatics, you're in equilibrium. Okay? Therefore, the electric field inside conductor equals 0, and therefore the net charge inside also equals 0. Now when we get to circuits, that's electrodynamics, and we have charge moving. So when we have charge moving, we must have an electric field inside. Otherwise, we won't get charge moving. Now, when we talk about circuits, we normally talk about circuits in terms of voltage or electric potential difference, okay? But that also implies that there is an electric field in the wire pushing those charges along, okay? It's easier to talk about it in terms of voltages instead of charge.
Mr. Bruin, when I
Yeah.
have that circuit not on, it's saying electrostatics, right?
That's correct.
So it
when
should be on, just on the outside of that wire?
yes. So
And then
if
when
there's
it
any
turns on,
net,
it
yes.
goes-
So like for instance, if you do this, here's your circuit, and you have a switch, like that, a real easy circuit. When you close the switch, there's an electric field, so all the charge is moving around, okay? And the electric field goes from positive to negative, okay? And so in our conventional fake current, our positive charges follow that electric field. Now in the reality of the world, the negative charges will go opposite to the electric field, right? Remember,
Yes.
this negative will get a force this way, right?
Yes.
And a positive would get a force this way. All right? So when we open this switch, what we really get is that the outside of this wire is all charged positive, and this wire is all charged negative, because remember, when you touch a negative object to a conductor, then they share charge, right? This side of the battery is negative, so when you touch it to this wire, it shares its charge. This side becomes negative. And when you touch this wire to the positive side, it shares the charge with the positive side, so it becomes positive. So the deal is that what we've done is essentially extend where the positive and negative end of the battery is, and then all we have to do is connect this, and then we have a difference in voltage here, and so we end up getting, then it all starts to move. All right? Weird indeed. All right, charge polarization, we've talked about that. Okay, discharging an object, grounding. All right? If I have an object that's charged up, say I charge this thing up, and it's all negative, and I'm holding it by the insulation right here, so it would stay negative, and I want to discharge it, then, well, if I touch it to me, then I share charge with it, right? Do you remember the condition for when you stop sharing charge? Wait a minute, hang on.
When there's no potential there.
Yeah, like, so this is, if this is negative, then this has a high negative potential, right?
Yeah.
So it has negative volts, and if I'm neutral, then if I touch it to my head, then I will share the negative charge until when? When does it stop sharing?
It's the same.
When what's equal?
The charge.
The potential.
Is it that when the charge is equal?
Potential.
The net charge, I'm just
Potential.
throwing it out here, I don't know.
All right.
Minor negative each other side.
Yeah, equilibrium.
Okay, let's say if this has 8 extra electrons and I touch it to this one, if they're the same size and I connect them by a wire, then 4 will jump over here.
The number of electrons.
So they will exactly share charge.
Yes.
But if I do this, and if I have this little one, 1, 2, 3, 4, 5, 6, 7, 8, and I touch it to this thing,
Ooh.
will only 4 go over?
No, more than that.
Why?
Because it has to have the same electrical.
More surface area?
Okay. There's a couple of reasons. The practical reason is to say, well, it has more surface area for them to spread out, right? They want to spread out, right? And so more of them will spread out to over here. Now, the equilibrium condition is that they're going to spread out until the electric potential here and the electric potential here are the same. Because remember, charge flows between objects of different potential, right?
Yeah.
Or they can, anyway. So you'll end up with way more over here than you have over here. Whoops. I'm creating charge here. I'm violating conservation of charge. Okay?
That will get you in trouble.
All right. Yes, that will get me in trouble.
Physics police.
All right. So there you go. That is the equilibrium condition when you touch objects is that they have the same electric potential when you're in electrostatics. Okay? So like right now, this thing, the electric potential is the same everywhere. Hey, that makes a good segue here. Look at this. So right here, everybody, if the electric potential right there is 100 volts, actually it'd be a negative 100 because I have a negative charge, then what's the electric potential right here?
I think it's negative 100 volts. Yeah.
It looks like it would be more than negative 100 volts, right? But if it was more than negative 100 volts, then what would happen?
There'd be movement.
There would be movement of charge. So this also is negative 100 volts. Okay, write this down. When you're in electrostatic equilibrium, for a conductor, there's no electric field inside, there's no net charge inside, and here's the last one. The surface is an, I can write it. Hope I wrote that right. Equipotential. It's an equipotential. All right? Meaning that the surface is all one potential. Because if it wasn't, like remember, if I have a spot here that's negative 100 volts and I have a spot over here that's negative 200 volts, all right, if I put a positive charge right there, which way would that positive charge want to move?
The 200.
It wants to go to more negative, right? And if I put a negative charge here, where would that one want to move? To more positive, right? Okay, does that make sense? All right, so if you have electrostatics, then these must be the same. So the surface of an object in electrostatic equilibrium in a conductor, then there's no difference in electric potential. It's an equipotential surface. I lost the word I was going to say. All right. Okay, last thing before we get into numbers. Induction. Do you remember the process of induction?
Yes.
Okay, we have 3 ways to charge an object. The first way is called friction. You take 2 objects that have a different affinity for electrons. They're different places on the, oh shoot, what do they call it? Triboelectric chart or whatever, is that what they call that? Triboelectric series, yes. Okay? Different affinity for how much they hold on to their electrons on the outer shells. And if you rub them together, then one will steal electrons from the other. And when you rub them together, you just give it a little more energy to make it happen faster. Okay? So that's happening to you now when you walk through a carpeted area and you got shoes on in the wintertime and you pick up a static charge and you shock people.
I don't know why, but Mr. Hackett's door always shocks me when I open it. Like, different
Always?
days, all.
You have different electropotentials.
That's right.
But you wash your clothes.
Shocks the end.
Okay, negatives move from one to the other, leaving one positive and one negative. Okay, so like this one would end up being positive, and this one would end up being negative. And you'd have conservation of charge. How much positive one is, the other one will be that much negative. Okay, conservation of charge. The other one is contact.
Wait, question.
Raising the bar.
Question.
Yes.
Doesn't that make a conductor?
What's that?
Like if you have a line of negatives and positives in this circuit, does that make a conductor?
It won't necessarily have to be a conductor for this to happen. Like for instance, if you take an insulating material and, well, like for instance, glass and silk, or a balloon and a cat, okay? All right? They're both actually insulators, right? If you take the balloon and rub it past the cat, or pick up the cat, rub it past the balloon.
To rub.
Bang the cat against
The
the
balloon
wall.
and the
No, cat. Cats work better. I was petting my cat this morning and shocking the bejeebies out of it just because it was cold. It liked it, but didn't like it at the same time.
Oh.
Per ouch, per ouch. All right.
Masochistic
All right.
cat.
So what happens is they have a different affinity. The fur and the material of the balloon. I don't know what that is, plastic or whatever.
Call it.
And we'll call it a polymer. And when they rub past each other, one will grab electrons from the other. Okay? And because they're insulators, they'll stay in that area where you rub them across. Like socks in a dryer.
I did not follow that. How do you?
Socks in a dryer. Okay, don't use softener. Okay? Wait a minute. Okay.
What?
Don't use
Possible.
Okay, don't use softener, because softener just coats the material with a conductive surface so that it will sort of, yeah.
Bet you didn't know that, huh?
Well, like the socks will be all sticky and stuck to each other, right?
Dryer.
Yeah.
That does the charge thing, right? To not statify your clothes.
Yes. Actually, they have stuff that you can, like if you have, like,
Dryer sheets.
yeah, like a dryer sheet, yeah, and you rub it on your clothes if they're all staticky stuck to you, and it'll stop.
I hate it when stuff comes out of clean like that.
Yeah. Wait a minute, there's another, okay. All right, so girls, combing your hair with a comb.
Oh yeah.
It'll stick to the comb and stick out.
Yeah.
Same
I
thing.
remember in like
Combing your
sixth
hair.
How
grade.
do you quit that?
How do you quit that?
Make it stop.
You put something in your hair,
Wait, what?
like aluminum foil.
I'm not gonna, I like my hair.
Friction, contact.
Induction.
Okay, we got friction. Contact is when you have two objects and you physically touch them or provide a conducting path between them. Like for instance, contact between a cloud and the ground during a lightning storm. There's a conducting path that appears. Called a lightning bolt, right? So there has to be a pathway for them to move through. Okay? So if you connect them with a wire, then charge will move from one to the other. They'll share charge until when? Until they're all the same potential, right? V1 equals V2. The electric potential in one spot equals the electric potential in the other spot. Okay?
There'd be big V.
Big V, not little v. Like for volume, right? Well, no. For Vermont. There you go.
Vermont.
All right, induction. All right, everybody. Here we go, induction. Here's how it works. You got to know this process. Okay, here's the simple version. Error. All right, so we've got this object. We bring a positive up next to it. When I bring a positive up next to this conductor, but don't touch it, close but don't touch, close but don't touch, what does it do to this conductor? It polarizes it. Negatives move over here, leaving positives on this side. Okay, now, it polarizes. So step 1 is bring this close. Step 2, polarize. Step 3, if I bring this back away, what happens? It goes back to normal, right? Same as it ever was. Okay, so I bring it close. Step 1. Step 2, it polarizes. Step 3 is I provide a pathway for these to escape. Now, all of you have had electronics class, right? So you know what that is? It's a ground, right? So you just supply a spot for it to go to. And so these will leave. Now, if I take this away now, what happens?
It is negative
It'll
now.
still have it.
You'll have a negative net.
It all comes back. Why does it all come back?
Wait, you have to take
I gotta get rid of the ground, right? Because if I take this away, well, they'll all just be pulled back with the negatives, right?
Yeah.
Okay, so I gotta bring it close, polarize it, escape path,
Take off.
take away the escape
And then we
path,
have a negative.
And then
now
leave them stranded.
leave them stranded. So what you're doing is you're driving off the charge you don't want. Think of it that way. Induction is to drive away the charge you do not want. Okay? So if this is negative, and I want to charge you negative, what do I do?
You come closer. Oh, wait. If what is negative?
If this is negative, and I want to charge you negative, Cindy, what do I do?
You bring it close to me, like right here or whatever, and then you're gonna give me. You want to put something else. Let's just say.
And wait a minute, this is negative, and I want to make you negative.
Can you just touch her?
I just go up and touch you. And they'll share charge. But if this is negative and I want to make you positive,
You come close to me.
then I got to do all this business of induction, right? I have to drive the negative off of you to leave you positive.
Then
Okay?
you'll attract.
So when you say induction, that implies that whole entire process. Okay?
That's a long.
All right. So here we go. Coulomb's law. Coulomb. I just like saying the name.
Run
Coulomb.
away. I think cool.
All right, now, I've added the absolute value signs on here just to let you know that the force from one charge on the other charge is the same size, right? So the force from charge 2 on charge 1
Equal and opposite.
is equal and opposite to the force of charge 1 on charge 2. They'll be exactly the same, but in opposite directions. Now, please be careful. I've warned you about this last year, and I'll warn you again this year, is be careful about the sign, this plus or minus sign, because the plus or minus depends on radial direction, right? So the force from charge 2 on charge, well, let's do this one first. The force of charge 1 on charge 2, the radius from charge 1 to charge 2, radius from this one to this one is that way. I have a plus and a minus object here, so that's going to be negative, right? So that's going to be negative, but negative means if my radius is plus this way, then the force is going to be this way. All right? So it does not imply directionality in the XY coordinate system. Okay? Because we just said this is a negative force and it's in the positive X direction, right? It's in the radial direction, which has no relevance in the XY coordinate system. So please be careful. It is really best for a lot of, well, for everybody really, when you start, is to just take the absolute value and draw a picture of what the direction of the forces are, because it can be confusing. Okay? Now there are some limitations on Coulomb's law. Number one, Coulomb's law only applies to point charges. And it only applies to a pair at a time. So if you have multiple charges, you have to apply this to all the different pairs. Okay, number 2, Coulomb's law is only good for static charges. Actually, it's pretty good for as long as the velocity is much, much less than the speed of light. It works really well. And limitation number 3. Since it only takes care of 2 at a time, you have to do the superposition of all the charges. So like for instance, if I had to charge 1, 2, charge 3, charge 4, and charge 5, and I wanted to find the force on charge 5, I'd have to do this 1, 2, 3, 4 times, find out the direction of those 4 forces, and then superimpose them with geometry, right? Or trigonometry. Okay? Which is a pain, but can be done. So let's try it.
No.
So here we go. Here's our first one. You have a charge right here. It's called Q1, and it is plus 25 nanocoulombs. You have a charge here at 2 meters. 2 meters. And that is Q2, and that is negative 10 nanocoulombs. And you have a charge out here at 3.5 meters, and that is Q3. Oh, sorry, that's Q naught apparently. Q naught, and that's plus 20 nanocoulombs. I want you to find the net force on Q naught, that's 1, and 2, derive an expression. Derive on Q1 for the sum of the forces on Q naught for distances 2 meters less than or equal to x less than or equal to infinity, and graph it. Okay? Oops, I didn't draw my other charges on there. Hang on. Here they are. Okay?
Is there gravity?
Okay, good question. Unless otherwise stated, or unless our object has a lot of mass, we will tend to neglect gravity always, just because gravity force will be so much smaller. And the reason why is because the electric force is K Q1 Q2 over R squared, and our K constant, which is 1 over 4 pi epsilon naught, is 9e9 Newton meters per Coulomb squared, and the gravity force is big G M1 M2 over R squared, and big G is 6.67 e to the negative 23rd, is that right? Newton meters per kilogram squared. Newton meters squared, sorry, per kilogram squared. I think it's negative 23rd, is that right? Negative 11? Oh, 23rd. What am I thinking? That's the wrong one.
Okay.
It's negative 11. That's right.
Oh, that's all.
So look at the difference between these constants. Okay? There's a huge difference between these constants. Okay? So even if you have something in nanocoulombs, which is 10 to the negative 9th, okay? And these things all weighed a kilogram, or had a mass of a kilogram, gravity's still going to be so small we won't have to worry about it, right? So, there you go. All right, you got to have your calculators out. It will really help you if you draw a picture. Yes, please, look. You do not have to use this constant epsilon naught, because 1 over 4 pi epsilon naught is 99. So whether, on our equation sheet, it's going to look like this. All right, but this is 99, just like it is over here, okay? I'm going to write it both ways because you'll see it both ways, but on your equation sheet, it's 1 over 4 pi epsilon naught. Now, we're going to find out in this class why it's 1 over 4 pi epsilon naught. It's not always going to be that way. Last year it seemed stupid for us to write down 1 over 4 pi epsilon naught because it was always 1 over 4 pi epsilon naught, which is always the same as k, right? But we won't always have that. Sometimes we'll have 1 over 2 pi epsilon naught, or sometimes we'll just have epsilon naught. It depends on the geometry of the problem. I don't know why it is, but these types of problems always seem to take forever. Okay, here we go. Let's do this a pictorial way because I think it helps a lot of students out. This will be my pink charge. This shall be the blue charge. Okay? The force from the pink charge on Q naught, which way will that be? Okay, this is a positive, that's a positive, so we'll get a force to the right. Because it's going to be a positive charge, which means repel along the radius, right? Okay, these two, this one's negative, that's positive. This one's going to give you a force to the left. Okay, so we got the pink force and the blue force. You need to solve this equation twice. Okay, Q1, Q2 over R squared. Now we got some number issues. 99 with units, Newton meters squared per Coulomb squared. We've got Q1, which is 25 e to the negative 9th coulombs, nano. We've got 20 e to the negative 9th coulombs for charge 2, and our radius is 3.5 meters. Okay? It is meters, right? Wow, because sometimes they'll put centimeters or something else in there. Okay, what does this come up with? By the way, this is force 1 on 0. What do you get? 3.67. E to the negative 7. Okay, so I'm going to put 0.367 e micro newtons. How's that? Sure. Is that okay? I'm going to call that positive or in that direction. All right? Okay, if we repeat this for the electric force from charge 2 on charge 0, what do we get?
Okay.
Now, just give me the answer.
Okay.
Negative 8 e negative 7.
Yeah, 0 like 799 micro newtons again, right? And that's in that direction, right? So our net force is going to be to the left. Okay? So we end up with a net force, Fe on charge 0 is negative 0.432 micronewtons. Everybody okay with that? And that is to the negative direction. Sarah, I'm going to put a little I here, right? It's in the negative I direction, to the left. Yes? Yes.
I'm confused on the directions.
Okay. This is positive. That's positive.
So why would
So this one is repelled from that one
right? Isn't that this way?
to the right. This one goes to the right
Right.
because of this one. Okay, this is negative and this is positive. So this one is drawn to the left because of this one.
Oh, okay. I thought you were saying that the negative was like going away from the.
No, I'm not even telling what these are doing, right?
Okay. I thought-
Okay.
Just add that.
I'm just looking at this instant on that one charge.
Okay.
Okay? Yes.
Instead of saying negative, can we just say which direction to go? Like if we feel more comfortable then. 'Cause-
Yes, I think most students will be better served when they solve this equation is to take an absolute value approach to this and worry about the magnitude of the force and then deciding the direction. I think you'll do much better.
Is that accepted?
Yes. Now, there will be situations where we'll need to put the sign in there and that will be important, but for like a problem like this, you're better off just taking the
As
absolute
long as
value.
you like show. Like,
Yes, but you need to draw a picture so you know what's going on.
Do we have to on the exam? Do we have to tell them like what direction we need assign?
Probably what they will ask is what's the magnitude of the force and give the direction. Okay? So what normally happens though is we get students getting it all messed up because, well, you know, they'll just take these positive and negative straight from the equation and add them together as they come out of the equation. And that doesn't necessarily give them the proper x, y direction. Does that make sense? So you're better off just making an absolute value, drawing a picture, figuring out the direction, and then decide whether you add them or subtract them. Okay? You're much better off. All right, so there we go. Now, here's the deal. I want an expression for what if this charge is moving someplace else? Okay? What's going to happen? So, we want an expression. And they could ask for this. So here you go. Well, we're going to have two forces, right? We're going to have the force, electric force of 1 on 0, plus the electric force of 2 on charge 0, right? That's going to be our net force. A net electric force on charge 0 is that. Okay? So here we go. From charge 1 on charge 0, we know that that one's always going to be to the right. We know the force from charge 2 on charge 0 will always be to the left in the negative x direction, right? So, I've got K, Q1, Q0 over, this distance is going to be a variable, right? I'm going to call it x squared. You okay with that? All right. Minus K, Q2, Q0 over, what's the distance between these two?
X minus 2.
Yeah, it's not going to be x. It's going to be x minus 2, right? X minus 2 squared. That look good?
I thought x was greater than 2.
But, like, we just want graph what's happening.
I want to see if x is somewhere between 2 and infinity. So this object is anywhere from here all the way out here.
Wouldn't it just be x?
So where is this object located? It's located at x. Well, how far is that from this one? The radius is x. So here, radius equals x. But here, radius does not equal x.
No.
It equals x minus 2.
What?
Because here's the radius. Right? There's my radius. And my radius is not equal to x. It's equal to x minus 2.
Okay. I thought that was like a number line kind of deal where you said that it was after the 2 meters.
Well, yeah. This one could be anywhere between here and infinity. Okay? All right. Is there anything else we need to do to that? Or are we done?
Do you want to plug in all those numbers?
Okay, now we could plug in all the numbers and we could factor a little bit out. You can factor K and Q naught out. You end up with Q1 over x squared minus Q2 over x minus 2 squared. And you can plug in the numbers and you can actually graph this if you want. Okay?
We have to go through all that, can we just leave it as?
It depends on what they ask. If they ask for a graph,
You will have to graph it.
you'll have to graph it.
No, I'm saying like, if they ask just for the equation, do we have to like, break it down to steps?
Oh, you could leave it like that
Okay.
if you wanted to. It's not a math test. So this is mathematically correct. There's nowhere to go from here but to simplify it mathematically, so you could leave it that way if you'd like. Okay?
I just thought it would have been more useful to make a function.
All right, if you just want to see what the function is going to kind of look like, all this out front is a constant, right?
You'd still have x squared here, 2 plus x.
And Q1 and Q2, if you just want to see what it's going to kind of look like, you could do this. Q1 is, just put 25 over x squared
So,
minus
wherever.
10 over x minus 2 squared. If you just graph that, that will give you the shape of the curve, right? Because the rest of everything is just constants multiplied through, right? Everybody do that. Get your graphing calculator out and just graph that. See what it looks like. And see if it makes sense. Because this is where physics C, E, and M is going to differ from mechanics. Remember, we're only interested in from here over, right? So what's our graph look like from here over?
It starts negative.
It starts at this 2 is an asymptote, right?
Yeah,
Why is it an asymptote?
because I'll never get there.
Because if this one was right on top of that one, the radius would be 0, and you'd have an infinite force here, right?
Explode.
Alright, so that's no good. Oh, sorry, you'd have an infinite force right here. Sorry. So you have an infinite negative force. So it comes over like this, and then somewhere over here it crosses over.
Yes.
Okay? Where's the crossover point? I get like 5.44, is that right? Our graph comes over like this, crosses over somewhere here
Yeah,
at 5.44. Okay? And then what does it do? It reaches a maximum and then goes asymptotically towards 0, right? Okay, now think about it for a second. What? Oh. Okay, think about this for a second, everybody. The graph starts off down here at negative infinity. That should make sense. If this positive gets really close to this negative, what should we get? We should get a really, really big, infinitely large force pulling it to the left, right? Okay, but think about if you're way far away. If you're way far away, a way longer distance than 2 meters, what does this look like, these two charges?
Nothing.
They look like they're real close together, right? And if they're real close together, first of all, if you're really, really far away, they look like nothing, right? And so what kind of force should you get? Nothing. Okay? But let's say that you're not really that far away. You still feel their influence. Which one's influence would you feel the most? The closer one, because you're closer because of 1 over r squared. But when you're very far away, when you're pretty far away,
The larger.
does the distance, radius distance here and here difference make a lot of difference anymore?
No.
Not really. So what you're going to feel is the larger charge, right?
We're pushing away more.
Yes. So you're going to pass a magical spot somewhere out here where when you're really close, the smaller one is more powerful.
So,
But when you get far enough away, the radius difference between these two is very little anymore, and so you're going to get influenced by the larger charge more. Does that make sense? That's why we have this positive section here. Because when you get right here at 5.44, you'll want to stay. You're in equilibrium. Okay, hang on a second, Andy. Yeah.
So if we were to push the charge from like 2 meters to like 5.5 and let it go and keep moving.
That's correct. So if we put the charge right here at 5.44, it would stay. If we put it a little bit inward, it would get sucked in. If we put it a little bit outward, it would be pushed away.
so unstable.
So we have an unstable, yeah, there's no equilibrium. Oh, we have an unstable equilibrium, don't we? Let's see. Because the force, yeah,
Force is 0 though.
right. We have an unstable equilibrium spot. That's correct. Yes.
Why does it really matter what force you feel more? Because when you're there, you're not going to be able to distinguish, oh, I feel the 25 or nano.
Well, okay. What we're going to start looking at is we're going to start checking some of our answers, because our answers are going to start looking like this stuff here. And we're going to look at them and go, oh gosh, what is that? Okay? And then we're going to have to start deciding, does this make sense? Because it's going to be hard for us to just look at it and see if it makes sense. So we're going to decide, okay, if we're really close, does it match up with what we'd expect? And when we're really far away, does it match up with what we expect?
Okay.
We're going to look at the limiting conditions to see if our answer is reasonable. Okay? So we should get a force of 0 when we get to infinity, which we do. And when we get a little bit in, but not too close, we should feel the effect of this one because it's a bigger charge, right? Because as you go away, like for instance, if you look at two people standing next to each other, when you're real close to them, the distance between them makes a big difference, right? Because you got to look over here, you got to look over here. But as you back away from them, all the way down the hallway, it looks like the distance between them gets smaller. Now the distance between them is not getting smaller, it's just the angle that you have to look through to get to both of them gets smaller, right? Same thing is going to be true here. When we get farther and farther away from these two, this difference in distance between them is going to have less effect. And so when that happens, you're going to see this charge more than that charge because it's a bigger charge. Does that make sense? All right.
That's why it's right.
Okay, let's do another one of these. This one
It
probably
has to
won't be
be
so
so.
painful, I hope.
No, no, it's the same.
Yeah, no, that's the exercise. 2009.
I was still putting 2007 over it hurts. I never got used to putting 09.
What?
All year he's been putting the wrong year.
Yeah, I barely got used to it, you know?
And now I have to change
Not
again.
to change again. I would put 07 because I like that year.
That's ridiculous. Would you like
See,
to
you're-
rectangle?
All right, so this is 5 meters and this is 10 meters. All right, find the force on Q3. What's the force on Q3?
Are you indecisive about those charges at the bottom?
Why? Oh, what the heck? Oh, that's dash. Huh? Plus or minus. That's right. Derive an expression for if it's plus or minus.
Which one's Q3?
Q3 is the top left.
That's a
Can't you tell?
No.
It looks perfectly like a 3 up here.
And the last two.
Well,
There you
as
go.
the distance
3
increases, you know,
one.
the angle we look through.
and 2. Wait a minute. Let's make a nice 2.
With the loop in it. Oh, no.
Oh, that's like a
Simple.
Y in the same.
Got a green charge and a red charge because it's Christmas.
So it's just.
Oh. Jingle bell.
The green charge. Which way will the green charge be?
To the left.
It will be down.
Down. There you go. There's your green force. Which way will the force be from the red charge?
To the left.
Down the diagonal.
Oh, bummer. That will be ugly. It's ugly.
All right. Oh,
So can we just do our answer at IJ?
All right. So technically it would be right, but if they ask for magnitude, you got to Pythagorize it, and if they ask for direction, you got to trigify it.
Trigger pad.
Kind of trigify.
Speak some word.
Just going off on a tangent.
Oh, bad. Very bad. All right, hurry. We're running out of time. We got stuff to talk about. All right, now you're just adding 2 forces, right? So you find the x and y components of the red force, right?
No, I mean, like,
Oh, which angle do I want? I'm sorry. Give it to me in polar.
polar?
So which quadrant will our final answer be in?
Third.
Third quadrant. Okay, the red force. The red force turns out to be how big? The red force is 0.1. Uh-oh, I get 1,080. Hey, you too, man. See ya.
Somebody just walked by.
1080?
Oh, it isn't even.
Oh!
Did you say P?
Mine is 1080 because I solved mine with centimeters. So it's going to be what? Point. There we go.
There we go.
All right, the green force. In my notes, I have 10 centimeters and 5 centimeters. That's why my number is different. And so this one is well, it's not negative. It's 0.0135. Is that correct?
No,
What?
that's not what I got.
You got it
I
wrong.
put it, I got 0.054.
I got what you got.
All right. I believe the people that believe me.
Nice.
All right. I claim correctness. Okay, now, which one of these do we have to break up? Okay, the red one. We got to find ourselves an angle, right? So, I don't know. Which angle you want? You want to find that angle?
Yeah.
All right, so that angle. That's 10 over 5 inverse tangent, or theta, tangent theta of 10 over 5 gives me a theta of what? 63.4 degrees. Okay, with that, I can take this thing and I can split it up into x component and y component. Because this is all in the y direction, right? And it's all negative y direction. This one's going to end up with a negative x direction and a positive y direction, right? So we've got to make sure we get our vectors in the right direction. That's why it's important to draw a picture. What do we end up with for these? We get 0.00483, is that right?
Yeah.
You're not even looking.
Yeah, that's what I got.
0.00 what?
Oh, that one.
38?
Oh, wait, no, that's
97? Yeah, I get 966.
Wrong angle.
All right. Now what the heck do I do with these? All right. The sum of the forces will be in the I direction and the J direction. What do we get in the I direction? That's X, right? That's Y, that's Y. So X is just going to be negative 0.00483. In the Y direction, we're going to end up with also a negative. Negative 0.0384-ish. Is that right? Ugh, lots of math. And then what do? Pythagorize it, and we end up with a magnitude of 0.00617 newtons at an angle of 218. Very good. 218 degrees. Okay, lots and lots and lots of math. Now,
Or if you just say 38 degrees in the third.
if you could, is it 30 degrees?
38.
38? Okay, you could say 38 degrees south of west, if you'd like. Or you could call it whatever the negative angle is from 0, if you'd like. Because some people don't like an angle over 180, because it's a little harder to immediately understand. That's fine. Or sometimes they'll ask you, like they'll have an angle marked, and they just ask you what the size of that angle is. All right, what's that? You got it? All right, here we go, everybody. Now, real quickly. Newton introduced the idea of action at a distance in 1687 in his book. Technically, it's pronounced Principia, but most people pronounce it Principia. Okay, this was a troubling concept. This is the first time we ever had action at a distance. And the only reason people believed it was because it was successful at describing gravity and because Newton had a lot of prestige, and so people believed it.
If it was like some wimpy little scientist, nobody would have cared.
Correct. If it would have been somebody that didn't have a big name for themselves,
Wimpy
a
little
lot of people
scientist.
probably would have thrown that idea away. But it worked. Anyway, so it wasn't until the 1700s, late 1700s, so like 100 years later, that this idea of action at a distance reappears in electromagnetism. Okay? Everybody sit. Stop sitting up. You're insulting me.
I'm sorry.
All right, now, here's the problem that we have, okay? Is this action at a distance is a real issue because Coulomb re-initiates the idea of action at a distance with his. That objects can apply a force against each other or between each other when they're not touching. Okay, here's the problem. If you've got a negative charge here and you got a positive charge here, looking at this charge, it receives a force this way, an electric force according to Coulomb's law. But if I move this charge from here to here, then the force will change from here to here. It will rotate. The question is, they're not touching. When does this one know that this one's moved? Does it know immediately? Or is there a delay?
Oh, that's smart.
Now, according to both Newton and Coulomb, it's instantaneous response. Now, this is a real problem. That means, like, if you're charged up and you run across the room, the people in the back of the room will know immediately.
So,
That's cool.
No matter how far away. Now, that was a problem. Does that make sense? That information travels infinitely fast from the one to the other. And the response is instantaneous. Okay? So, Michael Faraday, he was born in 1791. He was poor, almost no education. By the way, born in 1971, okay, we're talking,
1871.
I'm sorry, he was born in
Oh, okay.
He was born in 1791, okay? So after the Revolutionary War, he died in 1876. We're talking around Civil War time, okay?